Hello, everyone, and welcome to Unit 1 of Pre-Calculus Honors. This is our first set of notes here. This will cover Units 1.1 and 1.2. So what we're going to talk about today is going to be kind of all about functions. We're going to look at some definitions, some basics, some things that I know we've seen before, but something that is certainly going to help us throughout the course of the class. So right up top here, you're going to see there's a couple key vocabulary terms. Please go ahead and write these into your notes as I'm kind of explaining them. But a function is something that you certainly heard about before. Maybe it would have been, way back when where we talked about, these mapping diagrams where we had almost these eggs and each one would go to the other and you would say, yes, this is an input. This is a function because there's, certain lines that follow certain rules. But I really want to emphasize vocabulary this year, and we're going to start with these two. First, a function. A function is a relation between two variables where each input corresponds to only one output. So that's kind of the math direct definition, right? But what are we really talking about here? When we talk about inputs, it's usually, I would say 9 times out of 10, that's our variable x, and that's what we're going to start with our input. And our output, for the most part, what we'll see this year will be functions, so our output will be something like f of x. In other cases where we're not dealing with functions, we'll see later in the year, we could just get y as an output. But I know you've seen this before. Here's a quick example. Here I have just drawn up here. This is a function of x defined as x squared plus 2. So just to dig in a little bit deeper on this stuff, I know it's first day, but we want to make sure we're really understanding what's going on. So let's look at our formula here. What's in this parenthesis here, this is our input, this is our variable. You can see that our input in this case is x. As I said, that's our most common. What f of x is, all of this piece here, f of x is really defined as x squared plus 2. This is our output. When I plug x into this specific function, I get that value squared plus 1. And then f, let's grab red here. This is really just the name of our function. That f doesn't really do anything. It really just tells us which function that we've defined. So in this case, f of x is a function with x as its input and whose output is x squared plus 2. You can see here we'll see input and output tables. That's very convenient for graphing. And we'll also deal with quite a bit of graphing in the next few days. You can see here there's multiple ways to represent the exact same function. So that's a function. What else do we care about? Well, we also care about domain. And as you can see here, the domain is the set of all inputs, usually x, that are defined for a specific relation. So what do we need to worry about? Well, when we deal with domain, we don't want to divide by 0. Let's do no-nos. We don't want to divide by 0. Let's make sure we make it clear that we don't like that. So we need to be careful of any values that would cause us to divide by 0, that would exclude values from our domain. The other thing we don't like is if we have a square root of a negative number. That would also cause a domain issue. So the domain is a set of all the defined input values. Really, it's easier to focus on the values for which the function is undefined. All right, we got our definition squared away. Let's keep moving here. Here we have a graph. It's an example of what we call a piecewise function. So I'm going to write that in here. You should do the same. This is a piecewise function. The definition of a piecewise function is a function made up of two or more subfunctions, each with their own domain. So a piecewise function is a function made up of two or more subfunctions, each with their own domain. So here we have a graph of a piecewise function. We can see that there are really three parts. We can see that we have a linear function here, and we can see that this goes on infinitely to the left. We have a constant function here in the middle, and then we have another linear function going off to the right. So we have three different subfunctions in this piecewise function, but it's the whole picture is really what we're curious about. So question one, they want us to find the domain of this graph. Well, we just talked about domain. We said that domain is all the possible input values. And what we can see is that our domain goes over to negative infinity. We can see at this point here it's defined. It's not here, but that's okay because it's also defined up at the top. We're not defined here, but we are defined there. And then our graph again continues off infinitely. So our domain is all real numbers. The way we're going to write that, our default is going to be an interval notation. So what this means is in interval notation, we're going to write in parenthesis. We go from negative infinity to positive infinity. Most of us have seen interval notation before. We'll note that a few things here if you haven't. We use these parentheses to denote less than or greater than. I guess if we had this, it would be a greater than symbol, and this would be a less than symbol. We use square brackets if instead we had a greater than or equal to or a less than or equal to. This represents the interval of all the possible domains, so it's all the numbers starting at negative infinity, not including negative infinity, and going to positive infinity. The range is all the possible y values our particular graph can find. I'm saying y here because we don't really have a defined function, but all the possible y values, all the possible outputs. So what y values are achievable? Well, the highest point in our graph is up here at 3, and then everything else below it would be okay. So how would we say that mathematically? We would say that the range is all values less than or equal to 3. So the way we do this in set builder notation, it's a little different. We use these fancy brackets. And what we're really saying, well, let's write it first. So the set of all y values such that y is less than or equal to 3. So this set builder notation is maybe a little bit more familiar to how we usually describe domain and range. It has its benefits and downsides here, but the way we would do it here, we'd say all y values, and this vertical line here is we would describe as, such that y is less than or equal to 3. So why would we use set builder, say, over interval notation? Not all solutions, not all domains are intervals. So if I had all the integer values, I wouldn't want to list out all the integer values, 1, 2, 3, 4, 5. I would want to say something like all values such that x is part of the integers. So not all domains are intervals. When I don't have a range of values, when I don't have an interval, that's when set builder might be useful. Just as a note, interval notation is the default. Set builder will be kind of as needed. We'll use that more as we get into the second half of the year. So I want you guys to go ahead and try to use interval notation here and list the intervals over which the function is increasing, decreasing, or constant. I'm going to pause the video. You guys can go ahead and take a shot, and then we'll talk about it in just a few seconds. All right, let's see how our intervals went. So you can see here, I have all three of these answers listed. So a few things when we talk about intervals, we always talk about the x values. So I'm just going to put that here in my notes. When we describe intervals, especially, with one exception, we describe intervals unless it's regarding range. Those intervals are always describing the input or usually our x value. So where does our function, our piecewise function from our graph increase? Well, as we go left to right, we can see that we have a positive slope from negative infinity until x equaling 0. Now notice I have rounded parentheses here on both sides. When we have an interval of increasing or decreasing, that endpoint is neither increasing nor decreasing, so we're going to exclude it. Okay, so our interval for increasing goes from negative infinity to 0. Our interval of decreasing starts here at 2 and goes over to positive infinity, and that middle flat part is our constant section. All right, let's move on to page 2. And we are going to evaluate a piecewise function. Real quickly, I just want to make sure if you hadn't seen this before, this is what a piecewise function looks like. So we have our function here. We can see it's defined as C. Its input is H. And there's some stipulations, right? We follow one rule. If that H value, if that input is greater than or equal to 0 and less than 5. We have a different rule if that H value is greater than or equal to 5. Okay, let's actually figure out what this is describing, and then you're going to go ahead and try to interpret each of the following values. So parking in the city costs $8 per hour with a maximum cost of $40 for any given day. The cost of parking is therefore given by our piecewise function. So what I want you guys to go ahead and do is try to evaluate and interpret each of the following. What is the value of the function when h equals 3, and what does that represent in context of the problem? So I want you to go ahead and try A, B, and C on your own or with a partner, and we'll sum things up here in just a minute. Well, let's see how you did. You can see here A and B are complete. So C of 3 represents the cost to park for 3 hours, and in this case that will be $24. How do I know? Well, I know because H was on this interval here between 0 and 5, so this is the rule I use with my H value. 3 times 8 is 24. In part B, we're trying to find the cost of parking for 8 hours. Well, that is now on my second interval. H is greater than 5, so the total cost will always be $40. Now part C, hopefully you didn't overthink this. This is undefined. This value for our input is outside of our domain. And in real life terms, this would be the cost for parking in a parking lot for -3 hours. Obviously, that has no meaning, so it is undefined. Finally, our last piece today is going to be graphing a piecewise function. So we can see here a graph should indicate what rule is active for which part of the domain, and the graphs may not be continuous, so we just got to be careful at basically exchange points, where we jump from one rule to another. So what I'm going to do here is I'm just going to sketch in, oh, that wasn't very good. I'm going to go ahead and sketch in my my axes, my X and Y axes here. That makes graphing a little bit easier. Just looking ahead here, I can see that the domain I need, something happens at X equals 1. So what I like to do here, I really start by focusing on our domain. In this case here, something happens at 1. So what we can do is we can actually put a little dotted line there. Now this dotted line has nothing to do with the graph itself, right? It's not really demonstrating any values. It's not doing anything for us, but it does tell us that something changes. So when we're less than or equal to +1, let's use green. This is the rule we follow, x plus 2. That's a linear function, slope of 1, a y-intercept of 2. So that function would look like this. this other function, when x is greater than 1, we'll use pink for that one, it's always 4. So I can count 1, 2, 3, 4. And it's always going to be this constant function going horizontally to the right. Now, importantly, because of this symbol here, greater than but not equal to, we want to include an open circle at that point. So our graph, we can see now, is defined for all values. And we can see clearly that when the sub-functions change at x equals 1, we can clearly see which point defines the function. So we're going to pause there. We'll get into some more functions as we go. Nice work today, everyone.